Hello, I'm going to be discussing the Runge kutta method using Mathematica. I'll assume the theoretical knowledge is in order as always, and what I'm going to do is try to approximate the solution to this differential equation. It's a normal ODE with these initial equations, step size 0.2 within this interval. These are the Runge kutta formulae that we're going to use. These will become apparent in a bit. Right. So the first thing we want to do is define the function that we've been given. The function has two arguments, x and y, so we'll pass both arguments in the function. Right? And that's going to be a colon equals, so that's x plus y. So we can shift enter to run that. Right, the next thing we want to do is define our bounds. Now our upper limit, which I will call just a lowercase u, is 0.6, and our lower limit is 0. Now the step size we've been given as 0.2, and if we want to calculate the number of steps in the interval, all we have to do is subtract u minus l and divide that by h, and that will give us the number of step sizes. Right, but notice that the 3 has a dot in it. And for what I'm going to do next, we can't have a floating point number, and I'll show you what I'm going to do next. What I want to do now is define an array where I'm going to store all the x values and store all the y values. Right, so this is a fourth order, since this has 3 steps in this interval, we're going to have 3 solutions for x and 3 solutions for y. But we need an array that has 4 elements for each, because we need to store the 4th element will store the initial value. Let me demonstrate. Let's call our array for x, and we use a constant array where we say we want zeros of size n plus 1. We should get an error here, and as I said, because this constant array function only accepts integers, so we need to convert this 3 into an integer. So how we do that is, in this calculation that we performed here, we use a function called integer part, and there we go, and we rerun this, and now the 3 appears with no decimal point, and therefore if we run this now, we should have this array. So the first element in this array will store the initial value of x, which is 0, and the next 3 will store x1, 2, and 3 respectively. Right, we're going to do the same with the y, so I'm actually just going to copy this code and paste it. Just change that to y, and voila. But the initial value of y is not 0, it's 2, so we need to tell that to Mathematica, and we tell it that the first value in this array should be equated to 2. And now if we pass y again, we'll see that this value has been updated. Pretty standard stuff. Right, now let's get to the heart of the code using a for loop. In order to work out the Runge kutta coefficients, the k1 to k4, we need to work out this k1 to k4 for every step. So for the first step, we'll have k1 to k4, second step, and so on and so forth. So to do that, we're going to use a for loop, and we tell Mathematica that we want it to start at 1, from I equals 1 to I less or equal to n, and we want I to increment 1 at a time, comma. The curly bracket is not really necessary, but I'll just make the program look a bit better, so I just put it in there. Right, so let's start by defining k1. k1 is f of x1, y1, and remember we already have x1 and y1. These are your initial values. So how we're going to do this is we write there k1 equals the function f evaluated at well, the first element of the y and the first element of the x. So it's going to be the array x, first element in the array x, and the first element in the array y. and that's going to be our k1, right? And this will work. This will work for this particular purpose, but it won't work when I is equal to 2 or when I is equal to 3, because it will keep evaluating this at x1. And when I is equal to 2, remember now we'll need to use this value as the initial value, and so on and so forth. So we'll change this 1 to an I and that 1 to an I, so that when the I changes to a 2, we then get x2 here and y2. Hopefully that makes sense, right? And the rest that we need to do, if I close the function, that closes the function, right? The same will happen with k2. We define k2, so we need a semicolon here to indicate that we're still within the same for loop. We define for k2 using the exact same formula, so it's the function evaluated at the first x value, or x at I, plus h. And we've already defined what h is over here. So basically this is your x value of the function, and the y value, or the y argument of the function, is y at I, that expression over there. So we can pass yi times 0.5. Should have actually put a 0.5 times h over here. I don't know what I was thinking. As per the formula there, right? So times 0.5 times k1 and times h. It's really just copying down the formula, right? And k3 is going to be much of the same. We just changed that k at the end to a k2, not a k1. So I'm actually just going to copy the same code and use that, and we just changed that to 2. k4 is going to be a little bit different. It doesn't have the 0.5, so the halves, if you prefer to say it like that. So I'm just going to remove that part of the code and this part of the code, leave everything else as is, as per the formula. Right, so we've gotten our k1, k2, k3 up to k4. Now we need to update the y. So the formula states that y at I is equal to that, so we'll state that y at I plus 1. Remember, y at I is the initial value, so y at I plus 1 will be the value after that, which is the value that you're trying to work out, is going to be equal to y at I plus 1 over 6. You can use a palette for this, or a shortcut if you want to. I'm just going to do it the old-fashioned way because I don't like struggling. Plus k1 plus 2 times k2 plus 2 times k3, my keyboard tends to malfunction sometimes, plus k4. Right, and there we go. So then to update, remember now we still at x equals that. So for the next iteration, we need to tell Mathematica that now move to the next point of x. And how we do that is we tell it that the next value of x, or the next position, x at I plus 1, will be equal to the previous x value plus h. So what this does is, our initial value was 0. Now we're going to add 0.2 to it. Therefore, we've taken the first step. And the next time we'll add 0.2 to that. That's the second step, and so on and so forth. And from there, we can close the curly bracket, close the square brace, and let's run this, and hopefully there are no errors. Yep, no errors. So to see the solution, simply pass y, and it'll tell you that your initial value was 2, and these are the corresponding values, with this being the last y value that you got. So that's it. Like and subscribe. For some reason you don't like this video, still press the like button. If you've got questions, post it in the comment section and I'll do my best to answer them. Goodbye for now.